8D.More applications. 8.12 Rolling friction. Friction for rolling objects is not the same as sliding friction. When an object such as a wheel rolls, every point on the rim of the wheel is in motion relative to the surface on which it is rolling, except the point where the wheel touches the surface. If the point of contact were completely frictionless, then the wheel would just slide along the road surface and no external torque could be applied to the wheel to roll it. In the real world, some friction always exists between the wheel and the road, causing the wheel to roll. The wheel experiences additional friction because it adheres to the road, tending to stick as it lifts away from the surface. What is the magnitude of traction on a wheel of a vehicle that is propelled in some way? The applied force, FAP, can be either an external force such as push or gravity, or it can be a force internal to the vehicle, such as a motor or engine. Such forces can be represented as a force vector on the wheel in the direction of application. When a wheel turns, there is always some friction present as its axle rubs in its bearings. In a more complex vehicle, such as a car, there are many points in the car's drivetrain where friction reduces the force that the engine supplies to the wheels. The sum total of all these points of friction that retard the freedom of motion of the wheel, including the friction forces between the wheel and the surface over which it rolls, is called rolling friction, FVR. The magnitude of the net propelling force that the wheel applies to the road surface, Fprop, is the difference between the magnitudes of the applied force and the rolling friction on the wheel. Fprop equals Fap minus Fr. The propelling force can be represented diagrammatically by the sum of the external force applied to the wheel by the vehicle, pointing in the direction of motion, and the rolling friction force opposing the applied force, pointing opposite the direction of motion. Since Fprop equals Fap plus Fr, the method shown in Figure 8-23 does not introduce errors, and this notation will be useful in later chapters. The magnitude and direction of the traction force on the wheel depends on the source of the applied force and magnitude of rolling friction. If the applied force is a force external to the vehicle, such as gravity, then the traction vector is equal to just the rolling friction vector. If the applied force includes a torque on the axle of the wheel supplied by the engine, then the magnitude of the traction force is equal to that of the propulsion force in the absence of any externally applied forces. The wheel will not slip as long as the magnitude of the traction force does not exceed the maximum static friction that can exist between the wheel and the road. 8.13 Putting it all together. Now that you have learned the process of free body analysis, the property of inclines, and the effects of friction, let's look at several examples that combine all of these aspects. If you study them carefully, you will better appreciate how multiple forces acting on a system determine its motion. Use the following approach for analyzing inclined plane dynamics. Assign coordinate systems to each system element so that the x-axis is aligned to the sliding surface and pointing up the slope. If other inclined or horizontal surfaces are involved, the x-axis should all be oriented parallel to the respective surfaces and point in the same general direction relative to the motion of each system element. B. Resolve all forces acting on each element of the system into their components, relative to the coordinate system for that system element. C. Determine the maximum static friction possible for the two materials at the angle of incline. D. Sum the non-friction forces parallel to the sliding surface for the entire system and compare to the maximum static friction for the system to determine the dynamic state of the system. If the non-friction forces are less than F's maze, the system remains at rest. If greater, the system is accelerating. E. If the system is accelerating, calculate the kinetic friction. F-sum the x-component forces, including kinetic friction, to find acceleration according to Newton's second law. 8.14 Using forces to solve problems. How could forces prevent head-on collisions? One way is to install a barrier that uses forces to prevent cars and trucks from crossing the road into oncoming traffic. The familiar wedge-shaped concrete barriers in the medians of heavily traveled highways are called Jersey barriers, so named because they were first designed for New Jersey highways. Though apparently simple, their design is the result of a significant amount of testing and applied physics. Their purpose is to prevent injury to the driver and damage to the vehicle by using only the minimum force necessary to prevent vehicles from crossing into oncoming traffic. To do this, the barriers must provide the right amount of force at the correct angle. Typically, the barriers stand about 1 meter tall. They are made of white reinforced concrete and are anchored to the road. Their faces consist of a shallow sloped lower section and a steeply pitched upper section. See Figure 8-28. Often they are fitted with reflectors to increase their visibility. Since the installation of the original barriers in the early 1960s, many designs based on this pattern have been adopted by various states and even by other countries. Jersey barriers reduce accidents by forcing straying vehicles back onto the road in an upright position. If a car hits the barrier at a glancing angle, the wheels ride up onto the lower section with the shallow slope, thus turning the wheels and returning the car to the road with minimal damage. If impact occurs at a steeper angle, the car's front bumper will hit the steeply angled face, lifting the vehicle upward and reducing friction between its wheels and the road. The front tire then descends to the barrier's lower section, which redirects the vehicle back onto the road. If the distance between the wheel and front bumper is small, as with a passenger car, then these processes are almost simultaneous. The success of the Jersey barriers is indicated by the results. Highways that had Jersey barriers installed experienced a significant reduction of head-on collisions and a complete elimination of fatalities due to crossover collisions. After installing Jersey barriers in California, which has more miles of multi-lane highways than does any other state, there was a reduction of fatal collisions by 36% and of fatalities by 43%. Though not as fascinating as the more technological applications of physics, the design of these barriers is an instance of exercising dominion that achieves one of the best possible goals: preserving the lives of fellow human beings.